In mathematics, a Frobenius group is a transitive permutation group on a finite set, such that no non-trivial element fixes more than one point and some non-trivial element fixes a point. They are named after F.G. Frobenius structure. A subgroup H of a Frobenius group G fixing a point of the set X is called the Frobenius complement. The identity element together with all elements not in any conjugate of H form a normal subgroup, called the Frobenius kernel K. There is still no proof of this theorem that does not use character theory. The Frobenius group G is the semi-direct product of K and H. Both the Frobenius kernel and the Frobenius complement have very restricted structures. J.G. Thomson proved that the Frobenius kernel K is a nilpotent group. If H has even order, then K is abelian. The Frobenius complement H has the property that every subgroup whose order is the product of two primes is cyclic. This implies that its Solow subgroups are cyclic or generalized quaternion groups. Any group such that all Solow subgroups are cyclic is called a Z-group, and in particular must be a metacyclic group. This means it is the extension of two cyclic groups. If a Frobenius complement H is not solvable, then Zassenhaus showed that it has a normal subgroup of index 1 or 2 that is the product of SL2 and a metacyclic group of order coprime to 30. In particular, if a Frobenius complement coincides with its derived subgroup, then it is isomorphic with SL. If a Frobenius complement H is solvable, then it has a normal metacyclic subgroup such that the quotient is a subgroup of the symmetric group on 4 points. A finite group is a Frobenius complement if and only if it has a faithful, finite-dimensional representation over a finite field in which non-identity group elements correspond to linear transformations without non-zero fixed points. The Frobenius kernel K is uniquely determined by G as it is the fitting subgroup, and the Frobenius complement is uniquely determined up to conjugacy by the Shor-Zassenhaus theorem. In particular, a finite group G is a Frobenius group in at most one way. Examples. The smallest example is the symmetric group on 3 points, with 6 elements. The Frobenius kernel K has order 3, and the complement H has order 2. For every finite field FQ with Q elements, the group of invertible affine transformations, acting naturally on FQ is a Frobenius group. The preceding example corresponds to the case F3, the field with 3 elements. Another example is provided by the subgroup of order 21 of the collineation group of the Fano plane generated by a threefold symmetry sigma fixing a point, and a cyclic permutation tau of all 7 points, satisfying sigma tau equals tau squared sigma, identifying F8 asterisk with the Fano plane. Sigma can be taken to be the restriction of the Frobenius automorphism sigma equals x squared of F8 and tau to be multiplication by any element not in the prime field F2. This Frobenius group acts simply transitively on the 21 flags in the Fano plane, i.e., lines with marked points. The dihedral group of order 2n with n odd is a Frobenius group with complement of order 2. More generally, if K is any abelian group of odd order and H has order 2 and acts on K by inversion, then the semi-direct product KH is a Frobenius group. Many further examples can be generated by the following constructions. If we replace the Frobenius complement of a Frobenius group by a non-trivial subgroup, we get another Frobenius group. If we have two Frobenius groups K1, H and K2, H, then H is also a Frobenius group. If K is the non-abelian group of order 73 with exponent 7, and H is the cyclic group of order 3, then there is a Frobenius group G that is an extension KH of H by K. This gives an example of a Frobenius group with non-abelian kernel. This was the first example of Frobenius group with non-abelian kernel. If H is the group SL2 of order 120, it acts fixed point freely on a two-dimensional vector space K over the field with 11 elements. The extension KH is the smallest example of a non-solvable Frobenius group. The subgroup of is as an house group fixing a point is a Frobenius group. Frobenius groups whose fitting subgroup has arbitrarily large nilpotency class were constructed by Ito. Let Q be a prime power, D a positive integer, and P a prime divisor of Q-1 with dP. Fix some field f of order Q and some element z of this field of order P. The Frobenius complement H is the cyclic subgroup generated by the diagonal matrix whose ith entry is Z. The Frobenius kernel K is the solo Q subgroup of GL consisting of upper triangular matrices with ones on the diagonal. The kernel K has nilpotency class D-1, and the semi-direct product KH is a Frobenius group. Representation theory. The irreducible complex representations of a Frobenius group G can be read off from those of H and K. There are two types of irreducible representations of G. Any irreducible representation R of H gives an irreducible representation of G using the quotient map from G to H. These give the irreducible representations of G with K and the kernel. If S is any non-trivial irreducible representation of K, then the corresponding induced representation of G is also irreducible. These give the irreducible representations of G with K not in the kernel. Alternative definitions. There are a number of group theoretical properties which are interesting on their own right, but which happen to be equivalent to the group possessing a permutation representation that makes it a Frobenius group. G is a Frobenius group if and only if G has a proper non-identity subgroup H such that HHG is the identity subgroup for every G(G)-H, i.e., H is a malnormal subgroup of G. This definition is then generalized to the study of trivial intersection sets which allowed the results on Frobenius groups used in the classification of CA groups to be extended to the results on CN groups. And finally, the odd-order theorem. Assuming that is the semi-direct products of the normal subgroup K and complement H, then the following restrictions on centralizers are equivalent to G being a Frobenius group with Frobenius complement H. The centralizer CG is a subgroup of K for every non-identity K in K. CH equals 1 for every non-identity K in K. CGH for every non-identity H in H.